The fluid on the surface of the eye, called the tear film, plays an important role in keeping the ocular surface healthy. The purpose of the tear film is to lubricate the eye surface, transport waste from the eye, and protect against dust and bacteria. A thin or poorly formed tear film can cause problems such as dry eye syndrome. Symptoms may include gritty or dry sensation, reduced visual acuity, or inflammation. Symptoms of DES afflict an estimated 5 million Americans. There are many different factors that affect the human tear film. One of particular interest is the blink motion. During a normal blink, the upper eyelid descends over the eye, and during the upstroke paints a thin layer of tear film over the surface, allowing the tear film to reform. Much work has been done in creating mathematical models for the thinning of the tear film in simple geometries, but we aim to better incorporate the geometry of the eye and its motion. It is mathematically challenging to incorporate the curving and moving boundary of the eyelids. To overcome these difficulties, we simplify the corners of the eye for increased control of relevant mathematical parameters. To create our mathematical representation of the eye, we begin with a square box, which is then stretched to make a very long strip. We then transform this strip into an eye-shaped domain through a mathematical device called a conformal map. Once we have this eye-shaped domain, we are able to make it blink by specifying the motion of the upper eyelid. This process is advantageous to us since it allows us to link the square box, which is mathematically convenient, and the eye, which is physically realistic. Thus, we are able to solve our equations in the box and then move them to the eye to express them physically. Once we have implemented these transformations, we test them with a simplified version of the tear film models. Solving the test problem illustrates effects of incorporating the blinking eye. In particular, we see a layer of fluid build up on the upper eyelid during the downstroke, acting like a snowplow, as shown on the screen now. We can also see that the blink washes away any irregularities from the starting state and, in essence, resets the tear film. Our approach to simulating the movement and shape of the eye is highly promising. Moving forward, we will solve the general tear film equations on our blinking eye.